One of the standard criticisms of agile software development ecosystem is that this approach is just excuses for ad hoc undisciplined coding. All the elements presented on the slide are elements for developers who are exploring new ways of meeting the difficult goals of rapid product delivery, low defect levels, and flexibility. A principle of the Agile Manifesto is continuous attention to technical excellence, and good design enhances agility, saying that technical excellence is critical to high-quality software. Delivering low-defect code is critical over both delivery speed and ease of change. Density of a defect depends on how many lines of code has associated a bug. So from developer to developer, you'll find that done isn't done. For defect removal, you can use two strategies: multi-level testing and code inspections. So call for frequent testing in order to deliver working software each iteration. Agile approaches call for constant integration testing and frequent builds. Pair programming can be seen as equivalent of instantaneous code inspections. Agile developers may use less formal testing documentation, and they may depend more heavily on the development team for testing than on a separate testing group. But they are no less dedicated to removing defects than any rigorous development group. Traditional rigorous methodologies and software engineering in general focus on architecture, requirements, and design. Coding and testing are considered low-value construction activities. In these methodologies, the high-leverage activities are the upfront activities. The Agile methodologies reverse this and phases. This is a real difference, and one that individuals and companies will have to address when they consider Agile software development environment. Agilists believe in the restoration of programming, the actual production of working software, to a place of critical importance in the development process. All the Agile approaches advocate high quality through the use of short iterations, frequent builds, and continuous testing. But extreme programming goes further. XP promotes three practices, rules in one sense, that if followed generate complex behavior whose goal is technical excellence. These practices are simple design, automated test, first development, and refactoring. Simple designs require thought. Simple within the XP context takes on two characteristics: no anticipation of future requirements and easy to change. First, no anticipation means to develop code for the story at hand. Don't think ahead, develop a specific solution, not a generalized one. Second, a good design is an easy to change design, one in which the intention of the code is clear, one in which elements are minimized, and one in which there is no duplication. If we focus on coding the features at hand and not generalizing in anticipation of the future, then once the future arrives in the form of new features or stories, we can just add them to the code base. First, we examine the code and ask if the code looked like that instead of this. Could we implement the new feature more easily? To keep the cost of change low, we periodically redesign or refactor. This is a system of practices. Pick one practice, say simple design without refactoring, and the generative nature of the system disappears. Pick all three of them, automated testing, simple design, and refactoring, and emerging results, those larger than the sum of the individual practices, occur. Simple designs reduce testing work. Constant testing reduces delivering time. Interleaving testing and coding gives developer and testers a better understanding of the code. Having an automated test suite enables developers to refactor with less apprehension about breaking the system. Refactoring allows the design to emerge from the code, not be detected by meta models. Refactoring maintains simple design yet enables those simple design to evolve as functionality is added. Does this mean no anticipatory design ever? No, but it does mean balancing anticipatory design and refactoring. Traditional approaches place little if any emphasis on refactoring. Project teams may spend months and months doing the anticipatory design and none doing refactoring, because of course they surely got it right the first time. Maybe the database and user interface designs require a slightly different balance of anticipation and adaptation. By using these three practices, we can learn the right balance. Are we doing a lot of upfront design work? If so, maybe we spend too much time on it. Are we refactoring a lot of code? Maybe a little more design would have been advantageous. Refactoring may be the single most important technical factor in achieving agility. Everyone refactors, it's just the increment size and time frames that are different. Agile developers are saying refactor more often and on smaller increments in order to avoid refactoring later on huge increments with lengthy time frames. Furthermore, different components should be refactored on different timescales. Refactoring goes hand in hand with simple design. To some people, incremental and iterative development implies sub-optimization, and in fact this may be true in lower change environments. To these individuals, sub-optimization implies low technical quality and costly rework. Their argument boils down to, if you could do everything right the first time, up front, then it would be cheaper, better and faster. It's the if that runs full of reality. The upside of increments is constant feedback and quick wins. The downside is sub-optimization and costly rework. To the inevitable question of how to achieve quick wins and reasonable optimization, the agile response is skeletal modeling upfront, meaning feature-driven development, FDD, and adaptive software development, and also lean development, combined with refactoring, extreme programming. There are rising two questions here. First, how big is the bang, or how small is the increment? In deciding the increment size, how do we avoid the problems of poor feedback or poor optimization? Agilists think that the easier to solve the sub-optimization problem, that the path to technical excellence and customer satisfaction lies in short increments, refactoring, and just enough skeletal modeling. The concept of levels of abstraction has been part of software engineering for many years. It is part of all engineering work. Abstractions, high-level views of a problem space that hide certain details, might be documented in diagramming models with successful refinements, adding details to the model. The ability to abstract away from the details in order to create a good structure has been viewed as a path to technical excellence. There are two fundamental reasons why you create models. Either you model to understand an issue, or you model to communicate what your team is doing. Architecture is another form of abstraction. I'll place architecture into two broad categories: environmental and system. Environmental architecture involves decisions about the environment in which the project team must operate, from database and language to middleware and web server. Many of the decisions on environmental architecture are outside the scope of individual project teams. Existing systems, overall product architecture or cross-application and intercompany integration plans may constrain the individual project teams. This leaves system architecture decision, data schemas, program modules, and so on to the development team. No doubt environment architecture change, but at different time intervals than system architecture. There are three key factors in doing agile, architecture or modeling. First is recognizing and constantly reminding ourselves that plans are just plans. Plans change and models change constantly throughout a project. Second is to have the need to keep things simple and understand that refactoring will help recovery from oversight. Third is that the best way to manage upfront architecture work is to time box the effort, short time boxes. I place architecture in iteration 0 and define it as an iteration in which nothing useful is produced for the customer. In today's world, we might justify spending a couple of weeks out of 6 to 9 months project on working out a class structure, model or a data model, but not much more. Git lines are just that, but my experience has been that initial time box for iteration 0 of 1 to 2 weeks per 6 months of a project is a reasonable starting place. Models as a communication or thinking mechanism serve a useful purpose. However, just as when coding and testing become uncoupled and linearly related, coding is done by one group, testing by another, with a time delay between, modeling as a component of design and coding can become uncoupled and linearly related. When modelers know nothing about coding, there is a problem. When programmers don't test, there is a problem. There needs to be an integration and a balance. Don't model very long before coding and don't code very long before testing. Agile approaches are not anti-architecture or anti-modeling. A few weeks of upfront architecture planning can be effective in improving the goal of technical excellence of our software products. It's an interesting phenomenon. Technical staffs, by and large, hate to write documentation, and managers, although they talk about the need, hate paying for it. If it were really so important, managers would be willing to schedule appropriate time into projects to produce documentation, and they would be willing to fund technical writer positions to assist in developing documentation. Neither of these happens in any reasonable proportion to all of the talking about the importance of documentation done by managers. Typically speaking, Agilists are generalists. Rigorous software engineers tend to advocate specialization, although Agile developers realize that additional specialties and roles may be required, particularly as project size increase. Agile projects will tend to have fewer roles and specialties than rigorous projects. Let me tell you 3 things about the quality versus speed argument. The first one, most people talk in broad generalities about the need for quality, or few projects teams spend any time defining what they actually mean by quality. The second, speed and quality, the defect aspect of quality at least, are related but not in ways many people assume. And the third one, following the footsteps of lean manufacturing, Agilists' goals are to increase speed and improve quality. Quality may be important but is far from simple. Is quality synonymous with customer value or just defect levels? What does good enough software imply? While there is certainly a relationship between speed and defects, it is not an inverse linear one. I've been involved with some very fast, very low defect projects and some very long, very high defect ones. In the end, the most important thing may not be speed or quality or low cost or maintainability or whatever. The most important thing is what the customer wants. If the customer says, I need it by Friday, and we say, okay, so you can have it by Friday, but you'll only get a few screens, limited testing, and only 3 of the 24 business rules, and the customer says, okay, then we've been successful if we deliver that very limited function, somewhat buggy, working piece of software on Friday. Delivering buggy code may not be very satisfying for the developers, but it could be acceptable to the customer. We may laugh, but perhaps the customer is someone in marketing who needs to show major prospects something tangible, whether it works well or not. Finally, the traditional wisdom is that if we reduce defects to a minimum level, other characteristics like speed, customer satisfaction, cost will all improve. Agile utilize traditional technical practices, but they have fostered new ideas, new rearrangements of traditional practices, and a different perspective on how to achieve technical